If you put a spoonful of sugar in your coffee cup and just let it sit there, eventually it's going to diffuse throughout the whole solution, right? That's not across a membrane at all, right? So it's just going from an area where it's in a high concentration toward an area where it's a lower concentration. It can occur across a membrane, and if it does, we have to consider some other special scenarios if it occurs across a membrane. We talk about diffusion being passive, but that really is kind of not a good way to think about it. Passive might imply that there's no energy involved, which can be true. You can never move something without energy, right? It takes energy to move things. But there's no input of cellular energy for diffusion. So I don't have to add ATP or other cellular energy to allow these molecules to move. The energy that drives diffusion comes from the molecules themselves. It comes from the concentration gradient. Again, that idea of this vibrational kinetic energy. And the more of them you have in an area, the higher energy you have. The less you have, the less energy you have. And the system will move toward a state of lower energy. Now, because of that, energy is not destroyed in that process, it's released. And you should be fully aware of the fact, right, that diffusion is exergonic, because in the proton motive force, chemiosmotic ATP synthesis, we use the energy of the diffusion of hydrogen to drive the synthesis of ATP. So diffusion releases energy. It's exergonic. And the energy that gets released comes from that concentration gradient. So we can actually use diffusion to do work under certain scenarios, and we do. We use diffusion to allow us to transport other molecules. We use diffusion to make ATP and whatever. Now, I put this table up there, and I know you can't read it, but you can look at it in the PowerPoint or whatever. But this just basically highlights the general kind of properties or rules for diffusion. Simple diffusion across a cell membrane would be something that is small, nonpolar, right? Doesn't have a charge that can move across the phospholipid bilayer. It uses the kinetic energy of the concentration gradient. There's no input of energy that's needed. Because of that, they move from an area of high concentration to low concentration until we reach an equilibrium. And an equilibrium in this case would be an equal distribution of those solutes throughout whatever the solution is we're talking about. Or an equal distribution across the cell membrane. If we're talking about that, movement doesn't stop at that point. There's just no net change in the distribution after that, right? So equilibrium is when there's no more net movement across a membrane. Diffusion is always faster the steeper the concentration gradient. Why? There's more energy. So it's faster over a steeper concentration gradient. Diffusion is always faster over a shorter distance, right? If I were to open a bottle of perfume right here, front row is going to smell it before the next row, whatever. It's going to take longer for it to get to the back because it's more rapid over shorter distances. That's just because they have further to travel, right? That kind of makes sense. We know that temperature increases the rate of diffusion. Because what does temperature do to the kinetic energy of molecules? It increases it, right? So we're just basically pumping up that energy content. And diffusion is faster based upon the molecular weight of the substance that's diffusing. So something small, like hydrogen, is going to diffuse much more rapidly than something larger like glucose. Just because it's smaller, it's going to take less energy for it to move, and it will move quicker. So all of these rules are rules that, and as I mentioned already, it can either take place in an open system or across a membrane. All of these are general rules that we have to follow. Movement of molecules in our bodies across our membranes can't disobey any of these physical principles. We have to work within these laws of physics. And that's going to constrain the movement of some molecules sometimes. Sometimes we're just not going to be able to move it because I can't. There's too much of it over there already or something, or it would take too much energy to move it. Now, across a membrane, we have to consider some things that we already talked about. First of all, these things have to be small to go across a membrane. They have to be of the chemistry that allows them to dissolve in the membrane. The membrane permeability is really going to depend on the chemistry of that compound. Some things are very lipid soluble, so they'll move through very easily. Some things not as lipid soluble, and they move through slower. So there is this kind of membrane solubility that we certainly would have to consider. The more soluble something is in the membrane, the easier it is for it to move. the less soluble, the less easy it is for it to move. In fact, if it's insoluble in the membrane, it doesn't move at all, like an ion or something. So those are all things we have to consider that, you know, they're going to be characteristic of particular compounds. So we'll see in context when we talk about certain things moving, we'll talk about how some of these things are important in that. Now, it is important to be able to move some things across the cell membrane that are not soluble at all. And in order to move them, we mentioned it before, we call that facilitated or mediated transport. We need to have a protein that helps them across the cell membrane. Now, proteins do a number of things, right? We just spent a lot of time talking about how proteins can be enzymes. You're aware, certainly from anatomy, that proteins can be structure, like collagen, keratin, stuff like that.